So this session and all the previous sessions are mainly where we pick up different topics, technical topics, either from research papers or from different blog post articles or just generally system concepts, and we just discuss them or we try to implement them on stream. And today is a brand new session, so you don't have to have any pre-reading. This is the first session and the only session on roaring bitmaps. If you're in university, that's all the background you need, because through these sessions it starts from the very basics and then we get to the advanced concept. That's great to hear. The previous one is on sieve, which is a caching algorithm, and the whole session is recorded. I think that was done in 2 parts. But yeah, when you get the chance, do take a look. And if you have any questions, you can reach out on the Resources for Everything Discord channel. Thanks. Right, I think we are good to go on time. So once again, good evening, everyone. Thanks for joining in. So this is the final session for 2024 for the reading group. In today's session, we'll be focusing on a interesting data structure, which is used in a lot of distributed systems today, which is called roaring bitmaps. In my earlier message, you would have seen it's used almost in many Apache server projects. It's used by different search products like Millisearch and so on. And it's a very interesting data structure, and especially if you, and in later parts of this discussion, when we come to its internal design, you'll realize how that design actually helps it stand out from the existing solutions and why it exists. So with that, let's get started, and we'll start from the very basics, as I mentioned earlier, which is what is the problem statement that we're trying to solve? Like, what is roaring bitmaps fundamentally trying to solve? So what it's trying to solve is basically how to store a unique collection of integers efficiently. So we have all seen this problem before, even in university, right? That you have a set of numbers and you want to store the unique ones in some collection, in some list or some data structure. And the first solution that for all of us when we are seeing this problem for the first time is that you keep a list, a normal array or a list of those numbers. And every time you insert to the list or you delete from the list or you check if an item is in the list, all your CRUD operations, you have to iterate through the entire list to see if something is present or not. And again, there are small optimizations here that you could think of, like keep the list sorted so you could do a binary search and so on. But one thing we all agree on is no matter how creative this approach can be, it's not as good. It's not as efficient for large inputs and large use cases. So the natural question that we ask ourselves at that time is, can we do better, right? Can there be a better solution? Can there be a better option for us? And when we say, can we do better, we basically get 2 different common solutions that we see. And many people who are working on data structures or who solve algorithmic problems online will know these 2, which is hash-based sets and self-balanced search trees. So these are their technical names, but if you have coded in Java or C++, you would know hash-based sets as in Java as a hash set, or in C++, you'll know it as an unordered set. And just to remind everyone here generally how these things work. So if you have a hash set, you can take an input, put it through a hash function, and then based on the index, you put it in a certain place in your underlying list or underlying array. And there again, you have 2 options. You can make these linked lists, which is called separate chaining, or you can linearly put them in their place if there's a collision, which is called open addressing. So again, these words, again, we have seen them in university. And this is just a quick primer on hash-based sets, which is one of the popular options for storing unique collection of numbers. Another option, which we also see, is using a self-balanced search tree. So what does that mean? In languages like Java or C++, you would have seen a thing called tree set or set. And the way these things work underneath is they just maintain a tree, like what you see here in this diagram. And everything is in a balanced and in an ordered fashion. So if you're searching for something, say for example, you're searching for the number 4. You start at 5. So 4 is less than 5, so you go to the left. 4 is greater than 3, you go to the right, and you find 4 in the leaf node. So the normal searching techniques that we use. So this is just a figure of a self-balanced binary search tree because there are 2 children per node, but you can have more number of children and keep it as a search tree and so on. And that's another solution that's available to you. But there is a third option, which is not as popular or not as commonly known, but it is a very interesting option which is known as bitmaps or bit sets. So this option again, just like the earlier two, can let you store unique collection of items, and it does it very efficiently also. So to understand what bitmaps are, we'll just take a second here to understand the basic operation of a bitmap or the basic principle of a bitmap, which is in a bitmap, if the value of a particular bit is 1 or 0, that value signifies the presence or absence of that element in the set. So as you would imagine, if a bit is set, it's set to 1, it means that that item is present in the set that you're representing. If it's 0, it's absent. And we can take this also with a simple example, which is like this. So say for example, you have a set of 2, 5 and 6. How would you represent it in a bitmap? Very simple, very trivial. You just take 1 byte. In our case, we have 1 byte, so we have 8 bits indexed from 0 to 7. And the bits corresponding to these positions, 2, 5 and 6, we set those to 1. And all the others are left as 0. And with that, you have represented the set of 2, 5 and 6 in 1 byte as a bitmap. And if you have to check for something being present in the bitmap, it's very quick. Just check if that particular bit is set with a bitwise operation. If you want to add an element, remove an element, again, it's very quick, right? Simple bitwise operations which are constant time. And one important point here is that this example just uses 1 byte as input, but bitmaps can be several bytes. You can have 10 bytes, 100 bytes, like you can have an array of bytes, and you can use that for your bitmap. So this is fundamentally what a bitmap is. And this is the solution which Roaring Bitmaps improves upon, right? So keep this idea in your mind as we move closer and closer to the Roaring Bitmap internals. Now, the important question to keep in mind here is that when we see bitmaps here, right, it looks quite efficient. It looks quite good in terms of space also. You're just using 1 byte, at least in this example, and you're storing 3 items. And you could potentially store 8 if you fill all the bits with 1 in the edge case. But where bitmaps are really good compared to array, hash sets, and trees is one when most of the bits are set, and you can even express this mathematically. So this is the expression which is also given in the paper for Roaring Bitmaps. And what this simply means is that the items in your set, which is S here, is basically supposed to be more than the number of bits by 64. And what that essentially means is in every 64-bit integer that you store in your set, you're storing more than one item. And that is where the efficiency comes in. Because think about it, if you use the normal set like an array, hash set, or you use a tree or anything like that, in each 64-bit position, you'd have to store only one integer, right? But in case of a bitmap, you can store more than one integer in that same 64 bits. So that is where the efficiency of a bitmap comes in compared to the other options, that in the same amount of space, you can store much more information. And essentially, this is how they mathematically say it in the paper for a 64-bit system. So if it was a 32-bit system, you would say n by 32, because again, the total number of bits divided by 32 will tell you the number of 32-bit integers that you can have. And if the number of items you're storing in your bitmap is more than that, that means you're taking advantage of the bitmap property. You're storing more data than you could with any other solution. So with this, we know a couple of things, right? Till this point in our discussion, we know a couple of things, which is we know what problem we're trying to solve. We know the different ways that this problem is solved today. And we got a deeper dive into bitmaps, which is the particular solution that Roaring Bitmaps improves upon. And we even saw where bitmaps are better with this mathematical expression here. So now, when we come to Roaring Bitmaps, we need to understand what the issues with the existing solutions like bitmaps and so on is, which Roaring is trying to improve upon. And the issue is that if you take a normal bitmap, what happens is that you can have certain cases where you take a normal bitmap and you store data in it, which is making an inefficient use of that space. So say for example, we have a bitmap and we want to store 3 elements in our bitmap. And the 3 elements are 5, 1 million, and 1 billion. So I repeat again, we have a bitmap and we want to store 3 elements in our bitmap, 5, 1 million, and 1 billion. Now at this point, if you have to use a bitmap, you can imagine how many bits you will need to represent this set which contains these 3 elements. And you can imagine how much space is going to be wasted because there are going to be so much memory which is just going to be zeros, and just 3 ones are going to be there, 3 set bits are going to be there overall. So this is a big wastage of space. And to solve this problem, there are already certain improvements on bitmaps which existed before Roaring, and those definitely fix the space issue. So you could store 5, 1 million, and 1 billion very efficiently in a sort of bitmap representation. But the issues that those approaches had is that they were not very good for random access, which means that, say, for example, I took one of those existing solutions and I stored these three numbers 5, 1 million, and 1 billion. If I had to check if 5 is present in the set, if I had to check if 1 billion is present in that set, it would not be constant time. It would not be O1. It would actually be O of n. It would be linear time. So that is very bad for performance. So the existing solutions which fixed the memory issue of bitmaps had very bad time complexity. They were not at all efficient for common operations like insertion, deletion, or checking the presence. So because of those reasons, those solutions, though they are memory efficient, not time efficient, those are not good for a lot of performance use cases. And this is where roaring bitmaps make their entry. This is where roaring bitmaps make their big entry and they shine here. So to understand roaring bitmaps better, we'll work through an example now, which is we'll try to insert a value 5 into our roaring bitmap. And we'll work through the steps and we'll understand how the roaring bitmap works internally now. So before I move forward and we move into this example to understand the internals of roaring bitmap, I'll just quickly pause here if anyone has any questions, any doubts of anything we have covered so far. Sure. Got it. I think I understood the question. So I'll just repeat it here for the recording too, that if you are saying that you want to store 5 in a normal bitmap, how would it work? So the way it would work is quite simple. So let's come back to this illustration that we have here. I'll just zoom in a little bit too. So what we have here is we have 1 byte. So we have our 8 bits indexed from 0 to 7, and we just want to store 5. So in that case, what we would do is that we would, let me also change this to a empty byte as well. So we can start from the very initial step. So you take an initial byte, and initially the byte is all 0, which means there is nothing in that bitmap. There's nothing in that byte. So this is empty. You can think of it as an empty set. And now when we just want to input 5, only 5, what we do is we need to go to the 5th bit index. So in this case, here, so this is the 5th bit index, and we set this to 1. That's all. So corresponding to that number, we need to go to that index and set it to 1. And that means that that number is present in the set. That's it.
I'm not able to understand that. Here we have written from 0 to 7, but what exactly is this 0 to 7, these digits?
Oh, so these are the indices. So for example, this is the least significant bit of your byte. That's at index 0. And similarly, this is the next bit of your byte. This is at index 1. These are just indexes, like how you have indexes on your arrays. Similar to that.
Okay.
Yeah.
Oh, got it. Thank you.
Thanks. Right. So now, with this primer on bitmaps, what the other solutions on bitmaps offer and where they are not good, now we can proceed forward to going through an example to understand the internals of a roaring bitmap. So the first step that we will do is we'll take our input number 5, which we want to insert into our roaring bitmap. And what we will do is that we will take that number and look at its binary representation. So in our case, this is a 32-bit binary representation. So that's why you see a lot of zeros, because 5 is quite a small number for 32 bits. But what you need to understand here, and this is not the representation for 5, fixing that live on stream. But yeah, this is the representation for 5 in binary. And the point here, and this is the first place where roaring bitmap is different from other solutions that exist, is that it looks at your 32-bit number in 2 pieces, in terms of the 16 most significant bits and the 16 least significant bits. So you can imagine that it takes your 32-bit number and it looks at it as 2 smaller 16-bit numbers. That is the first thing you need to understand, that roaring bitmap is deconstructing your number into 2 parts, into 2 halves. And the reason why this is important is because it uses these 2 sub numbers or these two parts to do a two-level indexing, which essentially means there are two containers in which your data eventually is represented. And it's done like this. We take the first 16-bit number, which is the coming from the 16 most significant bits, and we use this to select one container. This is just used to select a container. That's it. And once we have selected a container, we take the LSB bit, the 16 LSB bits that we have in green, and we insert this 16-bit number into that container. So that is the two-step process, that the first 16 bits will tell us where to put the data, and the second 16 bits will tell us essentially what data to put in the container. So you can think of it in two words. One is telling you the location, and one is telling you the value that is going to be inserted. So this is the very first step of a roaring bitmap, that you deconstruct your 32-bit number into two smaller numbers, and then you insert your data, just the lower 16 bits of your data. The second part of this step, after which I'll pause for questions again, is the container. So I said that the MSB bits will tell you which container to put it into, and the LSB bits are actually the data which is put into the container. So the natural question is, what is this container, right? I keep using this word, what is it? So the container can be in two forms. Even in the paper, there are two forms that a container can be in. One is a normal array that we are all used to and we know very well. It can be a normal array, or it can be a bitmap itself. That container can be a bitmap on its own. So I'll go through both the containers individually now. So the first type of container is an array container. And as you would imagine, it's as you would expect, that you take your 16 LSB bits and you just insert them into your array in sorted order. So you can see here in this example that there are different elements in our array already. So 0, 1, 3, 20, all the way till 30 and 225. And all these elements are in sorted order. So this is one way that you can represent your container. The other way that you can represent your container is as a bitmap, which we have already discussed just some moments back. So you can see here again that we just have one bit per value that we represent, and you can see certain bits are set here, which correspond to, you can see in the array container. So the index 0 is set, index 1 is set, so value 1 is there, value 0 is there, value 3 is there in our bit set. So with this, we have these two forms of our container, and these two forms exist in certain cases. So initially when you insert data, that is initially your set is empty and you're inserting data for the first time, it starts off as an array container, which is on the left here. When the array container becomes very large, specifically when it becomes more than 4096, it becomes a bitmap container, which is over here on the right. And as you would expect, once the bitmap container becomes very small, that means it contains very few elements. Again, we go back to the array container format. When it's less than equal to 4096 elements, we go back to the array container format. So that's the way it works, your two containers, and in what cases you convert from one container to the other. So it's just a back and forth process. And the reason why this is done, because I'm sure you'll be wondering that why does this exist? Why can't it just be one container? The reason why it's done is basically for space efficiency. Initially, when you have few elements in your set, you can use an array, and arrays will grow or shrink as you insert data. We know this from C++ vectors or Java lists, right? That arrays or containers will grow and shrink as you insert elements or delete elements from them. So they're very efficient when you have less data. But the moment you have lots of data, right, you have lots of numbers that you're storing in your container, then using a bitmap is very efficient, because as we discussed earlier, bitmaps just use one bit per value. You can see just one bit to represent the value 1, just one bit to represent the value 3. So depending on the amount of data you're storing, we move from one container to the other. And this is the way these two containers work and how we change between them. So I'll just stop here for any question. I'll keep this here on screen. So if you have any questions about these two containers, or even the previous step of how we split the number, feel free to ask them now. Sure.
So like I want to ask that if we are storing suppose we are storing the numbers in an array, and so like there won't be any difference between like the bitmap or the array. Like if we are storing it in an array, so it will consume that much memory only. So like how the bitmap is used here?
Right. So the way it would work is, say for example, your container has only 10 elements. It has only 10 numbers. In that case,
Yes.
we would use the array container initially because, first of all, as per the conditions in the paper, the number of items in the set is less than 4096. So that is as per the paper rules. And the other reason, which is very important, is that the array here can grow or shrink as you insert elements. So, say for example, you have only 10 elements in your container, you would use only 160 bits, because 10 elements times 16 bits an element, that's only 160 bits. So you're very efficient that way because your container is using very little space. And only when only when your number of items is more than 4096 will you go to a bitmap container. So that way your upper limit of space is only 8 kibibytes. That is another constraint in the paper, which is that each container can maximum have this size of 8 kibibytes.
So, like in this array, like here we have some numbers written 0, 1, 3, etc. So,
Right.
like are these the exact numbers, the data which we are storing, or is it like the maybe the bitmap or something?
Oh no, so these are just example values that I have filled in. In both cases, like whether you look at the array bitmap or the array container or the bitmap container, in both cases are just example values. So here we have 0, 1, 3, 20, 30, and 225. And in the bitmap case also, I've just tried to represent randomly certain values in the bitmap. So you can see randomly index 2, I've set it to 0 to say that it's absent from the container, or 0 and 1 are 1, so they're present in the container, and so on. And another interesting point that I feel would be better to share here rather than later is that the reason also why we switch between these two types of containers is the number of elements that we can store. So, just to make this also clear with another example, is that if you see, we have a max size constraint of 8 kibibytes, right? This is from the paper, and the reason is mainly for cache efficiency. 8 kibibytes is not a lot of data, and it fits very easily into CPU caches. So it's good to keep your data small so that it can fit in your cache and access is very efficient. So that's where the 8 kibibytes comes from. But another point here is, initially when you have your array container and it grows to 4096 elements, if you multiply 16 with 4096, you get 8 kibibytes. So you have reached your limit actually at that point. So the amount of data that you could store, at least given this space constraint, you have done it 16 times 4096. But to make things more efficient, to store more data in the same space, you can then switch over to a bitmap container, because in a bitmap container, you can store a lot more data, right? 8 kibibytes is 8 times 1024. Each bit represents one element. So that helps even in increasing the amount of data that you can store. And that's the whole idea. That's why arrays are called sparse chunks, because you're using 16 bits per number, and bitmaps are dense because for every bit you're storing one number. So you can imagine the amount of compression that you get from 16 down to 1. So that is the conversion that happens when you're storing a lot of data in a container, and how we keep it within the 8 kibibytes limit. And just a few other quick points to mention here before we move to the next step is that, as you would expect, if you are inserting an element into an array container, it will be a bit slow. It will be big O of n in terms of time, because you have to keep the array sorted. So you can imagine there's initially a binary search to find where to insert it, and then once you insert at that index, you have to shift some elements around in your array. So that is O of n. But again, the authors mention that because the data is so small overall, it fits in the CPU cache. So it's very efficient for CPUs to do these operations because it's all inside the CPU chip. It's all on the cache. You don't have to go to RAM or to your disk, nothing like that. So it's very fast. So it's not expensive. O of n is not expensive in this case, is what I'm trying to say. And as you would expect for a bitmap, it's simply O of 1. You can find the index, that is the particular byte, and then inside the byte you can find the offset bit which you need to set or unset very quickly. It's just direct memory access. So it's O of 1, it's very fast. And now the next question which we'll be discussing about is, how do we convert between array and bitmap containers? Because now that we're familiar with these two containers and why they exist and when to convert between the two containers, right? We have that entire background. The next point that we would want to know is how to go from one to another, right? How do you efficiently convert an array container to a bitmap container, and then vice versa as well. So the way you do it, the easy one is, at least if you want to go from an array container to a bitmap container, I'll also zoom here a little bit. So if you want to go from an array container to a bitmap container, it's actually very easy. All you need to do is you create a bitmap of size 8 KB. So you have a that much large array with you. And what you do is that at this point, you will set each corresponding bit based on the array element that you have. So again, going back to that example that we discussed in the very beginning, right? Imagine that in your array container, you had the values 2, 5, and 6. So what you would do is, again, you would take your new bitmap and you would go to the positions 2, 5, and 6, and you would set them to 1. That's all you would do. So going from an array container to a bitmap container is very easy. Start from an empty bitmap, go to those particular index positions in your bitmap and just set them to 1. That's all. So that's the easy one. The tricky one is if you want to go back. That means you already have a bitmap container and you want to go to an array container. So from individual bits, you want to go to actual 16-bit values. So how do we do that? So the paper notes an interesting algorithm which I'll be deconstructing just down below. So there's no need to be surprised or afraid of this algorithm. It's very simple. So this algorithm is very special in a way because it's very efficient to do for a CPU. It's very fast. You can imagine every iteration of this loop just takes 1 or 2 cycles of the CPU. It's that good. And that's why it's also mentioned in the paper so specifically, because it helps you very quickly go from a bit representation back to a numerical number representation. So without any further ado, we'll look at the individual steps of this algorithm. So I've just zoomed in on the same picture that we had on top. And these are the main steps that you need to look at. That is from lines 4, 5, 6, 7, and 8. These are the 4 lines, if you can see. So these are the 5 lines that if you see, you'll understand the entire algorithm. So let's begin with line number 4, which is just saying while w is not equal to 0. So w is our input integer. You can imagine it is one of the elements of our bitmap. It's one of the bytes of our bitmap essentially. So we take one byte of our bitmap, which is called w. And while it's not 0, that means while there is some set bit inside of w that we need to extract, right? We need to continue this loop. That is step number 1. Step number 2, which is on line number 5, which is this bitwise operation, t is equal to w and minus w. So what this bitwise operation is doing, very, very fundamentally what this operation is doing, is it's just isolating the least significant bit, set bit of w. So just to take an example here, right? If w is, say, this number, right? Then the value of the number doesn't matter, but the bit representation matters. That's why I've shown that over here. So you can see it is 1100. That is w essentially, right? What is t? T is just going to be the least significant set bit. That's all. Everything else is 0. Just the least significant set bit is going to remain. So that's what this step number 5 on line number 5 is doing. It is just isolating the least significant set bit. That's all. Step number 6, which is on line number 6 here, is just appending t minus 1 to s. So what is t minus 1? The bit count of t minus 1. So t minus 1 is essentially the positions, the bit positions behind the set bit, the least significant set bit. So you can see this over here again. If t is the isolated least significant set bit, t minus 1 is just setting all the zeros behind it to 1. We are just taking the zeros that are to the lower part of that 1 and we are setting them to 1 instead. So you can see the conversion here that we have done. And bit count, which is a very special instruction, and it's a very new instruction actually for CPUs. It has come out since 2008. In almost all CPUs today you will find this instruction. And the reason why it is very special is that it allows you to do an operation which earlier was very expensive for CPUs. And you can do it in just one cycle. So the operation is basically this. Let's say you have an input like this. This is a binary input. Again, the value doesn't matter, just the bit pattern matters. What the CPU can do now, again, since 2008, if you take almost any CPU has this instruction. In one cycle, in just one CPU cycle, with this instruction, it can tell you the number of set bits. So here if you count, you can see there's 1, 2, 3, 4, 5. There are 5 set bits, and the CPU can tell you in one cycle how many set bits are there now. So this is a very important instruction because it's used in the paper. It's used in this algorithm which is called bit count. So we take the bit count of t minus 1. So the bit count will tell us 2 because there are 2 set bits here. And that, if you actually notice, is the index of this 1. So just to zoom in over here, when we do the bit count of t minus 1, we get 2, right? Because there are 2 set bits in t minus 1. What you'll notice is that 2 is actually the index of this 1, of the least significant set bit, right? Which we see in t here. And this is how you can extract the index from W, the individual set bit indexes from W. So we first find the least significant set bit. We find out what the set bits before it are. So we make the 2 zeros into 1s. And then we do a bit count to get the count of the 1s. And that will tell us what the index of the least significant set bit is. So in here also we saw bit count was 2. So the set bit index, the least significant set bit index was 2 here. And the final step before again I stop for questions is that once we have found the index of the least significant set bit, right, we should remove it because we are done with that set bit. We found its index, we are done with it, so we need to remove it. How to remove it? That is step 7 on line number 7 here, where you do W and W minus 1. So this is the way it works. So what you do is you take W, which is the original number, and you do W minus 1, which essentially makes the least significant set bit into 0. You can see the least significant set bit is here, what I'm hovering on. When you do W minus 1, it becomes a 0. And when you do an AND operation, a bitwise AND operation, you can see we have removed the least significant set bit. So you can see in one cycle of the loop, what we have done is we have found the least significant set bit, that was t. We found the index of the least significant set bit, that was with the bit count operation and with t minus 1. And finally, what we did was we removed the least significant set bit because we processed it. We found its index, we are done with it, we removed it. That's all. And that is one iteration of the loop. And we keep doing these iterations until W becomes 0. That means we have extracted all the set bit indexes from W. So you can see here from this example that indexes 2 and 3 were set, and that is what S is. S is just a list of numbers, a list of indexes, and you can see S just has 2 and 3 because index 2 and index 3 were set. So that is all this algorithm does. It's nothing more than isolating the bit, extracting the bit position, and then removing that bit position to 0 so that we can move on to the next set bit after it, and then returning the list of indexes. Those are all the steps that this algorithm does. It just looks complicated because of the bitwise operations. So with that, I'll again pause here for questions. Any questions on this algorithm or this type of instruction that was introduced, which makes CPUs very fast for calculating the set bits in a number? Any questions, feel free to unmute and ask. All right, I guess there are no questions. If everyone's okay now, thumbs up. Okay, that helps. If everyone's okay now, feel free to put a thumbs up on Discord. It's just a reaction on the bottom left. That always helps in knowing everything's going good. So right, so with this algorithm out of the way, right, we can move on to the next step, which is, and let me zoom out here so that we have a overview of what we just completed right now. So now we know how to go from one type of container to another, and we know how to do it very efficiently. And I think that is the main highlight here, because even in the paper, right, these operations are kind of trivial if you think about it, but making them efficient, that is really where the genius of the authors come in. And you can see here, even with this bitwise algorithm that we just understood now, you have to really not look at the steps in terms of code, but you have to understand what the underlying meaning is. So for example, step number 5 was just doing what? Isolating the least significant set bit. Or step number 6 was doing what? It was just getting the index of that least significant set bit. So that is one of the interesting things that I also found in this algorithm, that you can't look at the steps and just figure it out. You need to understand what the hidden meaning is, that what are you trying to do by doing these bitwise operations. So that is always an interesting one, and this paper has this quite well. Now that we know about the containers and everything else, right, the next question that we should ask ourselves is that now that we know about roaring bitmaps, we know about their internals, we know about the containers, we know all of that, right? We can even probably write our own roaring bitmaps now. But what can you do with it? Once you write it, what can you do with it? So there are certain operations that you can do with roaring bitmaps, which you would expect from any set, whether it's a hash set or a tree set or a bitmap, whatever, you would expect these operations. So for example, your read operation to check if data is present, your insert operation to put new data, or even the delete operation to remove existing data from your set, right? All of these operations you would expect that support should be there. But roaring bitmaps can give you operations also like union. So you want to do union of two sets, you can do that, and even intersections. So these operations here that I am mentioning, contains, insert, and delete, these we have covered in the previous sections on the array containers and the bitmap containers. The operation again would be very simple. So if you want to take, for example, the insert operation, what you would naturally do is that you take a number that you want to insert into your bitmap. So I'll just come to this diagram here and explain. So say you want to insert any value, take your number, split it into two 16-bit numbers. The most significant 16 bits will tell you which container to go to, and the least significant 16 bits are inserted into that container. And obviously you have two types of containers, array containers and bitmap containers. You insert your data into the respective container and you make sure the size constraints are respected at all times. That if the data is too much, go to the bitmap container. If the data is less, go to the array container. That's all. And similarly for delete and even for contains, the operations would be very similar. So at this section of the discussion, the operations that I want to cover and I feel are quite interesting for everyone here is the union and intersection operations. So the union of two roaring bitmaps and the intersection of two roaring bitmaps. So let's jump into that now. So first I'll cover the union operation because that is actually simpler of the two. Because if you think about it, what is a union? You're basically combining two things together. It's an additive operation. You're adding things together, you're combining things together. Things are really going to increase. There is not going to be any reduction or decrement happening, right? It's all going to increase, increment. So when you have a union, especially in roaring bitmaps, what you also need to think about is you need to think about the container. Because we discussed there are two types of containers, right? So you need to be able to handle a union for any combination of containers. Array containers with array containers, bitmap containers with bitmap containers, or even array containers with bitmap containers, the heterogeneous case essentially. So we'll go through each of the three step by step. And the cases here are, we'll start with the array with array situation. So you have two array containers and you want to take a union of them essentially. So the way it would work is like this. I'll just zoom in here and we even have a diagram to help out. So when you're merging two arrays or two array containers together, the first thing that we need to recall is that these two arrays are sorted. Both the array containers always are sorted. That's the way roaring bitmaps are. So if you have two sorted arrays and you want to merge them, you may recall from your merge sort algorithm which you have learned in university, you know there's a merge operation that is done. That is exactly the operation which roaring bitmap also uses. So if you're merging two arrays, we know they are sorted because it's roaring bitmaps. So we use the merge operation. So these are, you can imagine these are your two input arrays and we are merging them. So this is just a snapshot of a merging process. You can imagine these two are sorted, which they are. We have our two pointers to track how much of both of the input arrays we have processed. And this is our final output array where we have already put certain data from both the input arrays in a sorted order. And again, as you would expect, we have to respect the size constraints. So for example, if the union is more than 4096, we need to convert it to a bitmap container. And we also know how to go from an array container to a bitmap container. We saw that in the previous section. It's very simple. Just take an empty bitmap. Every element in your array container, go to the corresponding bit in the bitmap container and just set it to 1. That's it. So that is arrays with arrays, the union operation. When you come to bitmap with bitmap, and I'll come to the middle one in the end because that is easiest to understand when you understand the other two. If you're doing a bitmap with a bitmap, right, the algorithm is basically like this. Each bitmap, again as we saw earlier, is of size 1024 because we know it is always going to be 8 kibibytes. That is a fixed size as per the roaring bitmaps data structure. So these are two fixed size arrays of the same length. So you can again imagine now that merging them is going to be so simple, right? You go through every byte of both the input bitmaps and you do an OR operation, because OR operation is basically going to merge the two bytes together, right? Because we all know how bitwise OR works. 1 or 1 is 1, 1 or 0 is 1, 0 or 1 is 1, and 0 or 0 is 0. So that's the merge operation that you can do with a bitwise OR, right? So if any of the bitmaps have the value, it will come into the output bitmap as well. And that's exactly what they've summarized here in this algorithm as well, which I've taken from the paper, which is you have a new bitmap, which is C. It's a fresh empty bitmap. It is again same 8 KB bytes in size. And we go over each of the 64-bit integers and we just do a bitwise OR of our two input bitmaps. Just do a bitwise OR and you can keep even the cardinality count. So cardinality count is the number of items in your set. So if there are 10 items in your set, 100 items in your set, it's just a count for that. And again, we're using the same bit count operation. That is the number of set bits. So that's what we're doing here with bitmap. Now the final case, which I'll just zoom into here again, which is array with bitmap. After this, I'll again open for any questions on the union operation. Is that, and this is and I'll start with this fun fact here at the bottom from our expert. And this is actually an interesting fact, which is if you take a union of an array container and a bitmap container, the result is always a bitmap container. I'll just repeat that again just so that everyone gets a moment to think why this is true. If you have an array container and you have a bitmap container and you union them, it will always be a bitmap container. The reason is because union operations are always additive, right? It is either going to stay the same, the cardinality, or it's going to increase. Those are the only two things that can happen in union, right? So if one of your inputs is a bitmap container, you know that there are at least more than 4096 elements that are going to be in your result because those are coming from your bitmap. So the result has to be more than 4096 elements. So that means your output also has to be a bitmap container. It cannot be an array container. So this is an interesting observation which makes performing the union of array and bitmaps very easy. Because what you do is you create a copy of the bitmap, the input bitmap, because everything in the input will be there in the output. That's how unions work. And then you just iterate over your array container, the other input, which was the array container. You just iterate over that, and each element of your array just set the corresponding bit. That's all. So this is why array and bitmap container unions are so easy, because this observation is very important. When you take a union of the two containers, the cardinality of the set is always going to be more than 4096 because bitmaps have more than 4096 elements in them. And unions are additive operations. The number is only going to increase. It cannot reduce. So you know the output has to be a bitmap. It cannot be anything else. So essentially what you land up doing is you're just taking the elements of your array and setting the corresponding bits in the bitmap. That's it. It just lands up being a simple for loop. So with that, I'll just zoom out here and I'll pause for any questions on the union operation of roaring bitmaps.
Array, we have B in the stored in that array, and we want to merge it with a bitmap. So will it be like the bit in the bitmap? The bits of 3 digit will be set to 1.
Right. So just to repeat again the question for the recording, the idea is that say you have an array container and a bitmap container, and in the array container you have the value 3, and you want to insert that into your bitmap container to do the union operation. So what you would do is very similar to wait, I think this is extra. Okay. So what you would do, I'll just go back to the diagram in the very beginning. This diagram always helps explaining the question. So what you would do here is very simple. You would take a copy of your input bitmap container. So say that your bitmap container had the values 2, 5, and 6, right? Let's assume that the input to the union operation from the bitmap container was 2, 5, and 6. And your array container only had the value 3. So how do you take 3 and you put it in the result? So going by the steps that were mentioned earlier, first you take a copy of your bitmap. So what I'll do is I'll also take a copy. So this is my input bitmap. I will take a copy of it, Control C, Control V. So that's my copy. And then what I will do is I will take the bit position for 3. So that is basically index 3, the index bit position 3, and I will set that to 1. And this will be the result of my union. So I'll even make a new set here just for making things clear. So we have our set 3, which is our array container. And we had our bitmap, which is containing 2, 5, and 6. When you take the union, this is the output that you get. So I can even mention it as output bit values.
Got it. Thank you.
Perfect. So this is the so what we have covered now is the union operations, and in mainly in all the union and even intersection operations that we'll discuss now, the only thing you need to keep in mind is the fact that you have two types of containers. That's it. And you may have to deal with cases where you have heterogeneous case where you have an array and a bitmap that you need to take a union or intersection of. Otherwise, things become quite straightforward. So this is the union case once again. All the three: array with bitmap, and bitmap with bitmap. So with that, we come to the final operation that is covered in the paper, which is intersection. So when we talk about intersection, again, we have the same three types of containers. That doesn't change. Arrays with arrays, arrays with bitmaps, and bitmaps with bitmaps. So we'll start with the simplest one, which is arrays with arrays. And again, the same observations apply as we saw earlier, that the arrays are always going to be sorted because that's the way bitmaps, or specifically roaring bitmaps, are. So if you're going to have two sorted arrays and you need to take the union, you can just use a merge operation for merge sort. It's as simple as that. So you can imagine here that, say for this case, just to make it a bit more engaging, say for this case we had 5. So you can see here that both the inputs had 5 in them. But 5 should only show up once in our output because that's what the intersection is all about. And you can do that with the same merge operation that we use for merge sort that we have seen in university. So it's the same operation, but we can use it even for intersections, just like we did for unions. So that is arrays with arrays. Now we come to again arrays with I think bitmaps with bitmaps would be better. So again, this is a photo of an algorithm from the paper, and it's very simple. I'll go through it step by step, just like we did for the previous two as well. It's very simple when you understand what it is saying. It's just your normal 10 lines of code. That's how much it took me to implement it in Python. So what we are essentially doing here, right, when we look at this algorithm, is a few key steps. And I'll lay out the key steps before we look at the individual lines of this algorithm. What we are doing first is we want to know what the cardinality of the output set would be. So what does that mean? If I have two input bitmaps and I do an intersection of the two bitmaps, how many elements will be there in the output set? That's all. How many elements will be there in the intersection result? That's all is the question I'm asking. And that is what I'm calculating as my first step as part of this algorithm. Now, as you would have guessed, the reason why I want to know how many elements will be in my output set is because that will tell me what container I need for my output. So for example, if the intersection is less than equal to 4096 elements, then I know that I need to use an array container. But if the intersection has more than 4096 elements, then I know I need to use a bitmap container again, right? So it's just for that reason that I want to know how many elements will be in my intersection result so that I know which container to use to store the result. That is the only reason why I'm doing this operation. And that output, that the number of elements in your output intersection result, is stored in the variable C. So I'll just zoom in here again. That is stored in the variable C. And you can, and just like what I said, you can even see on line number 6, we are checking if C is greater than 4096 or if it is less than 4096. And accordingly, we are using a corresponding container. So on line number 7, where we have C greater than 4096, you can see we need to use a bitmap container for the result essentially. And you can see here that we create a new bitmap which is called C of 8 kibibytes. Then we go over each of the 64-bit integers and we just do a bitwise AND, because again, you know that if you're doing an intersection, it has to be present in both the input sets, and bitwise AND only works when 1 and 1, because 1 and 1 is 1 in the result. Otherwise, it's always 0. So that will help you get the intersection, and then you can return the result C and the cardinality also. Cardinality we saw, we calculated it earlier itself, the number of elements in the intersection result. On line number 11 is the other case where, as you would imagine, the intersection has less than or equal to 4096 elements. So we need to use an array container for the result. I repeat, we need to use an array container for the result because the intersection has less than 4096 or equal to 4096 elements only. So that is what on line number 12, we create an empty array of integers like a normal vector in C++ or a list in Java of integers. And what we do is that we go over each of the 64-bit integers in the input set, and we do a AND operation, just like we did for the bitmap case. We do an AND operation to get the intersection. And once we get the intersection right, we apply the algorithm 2, which we discussed earlier, to get the indexes of the set bit in a number. I'll just show you the algorithm also just to make things familiar. So we discussed that algorithm here. This is algorithm 2. So we discussed this algorithm earlier, which all that it does is you give it a bit representation or a bitmap, and it'll tell you the indexes of the set bit. It'll tell you what bits are set based on their indexes. So what we do when we are taking the intersection of a bitmap container with a bitmap container, if the result has less than or equal to 4096 elements, what we do is we first do the AND of the two bit representations, and then we append the set bits, which we get using algorithm 2, into our array of integers, into our result D, and we just return D. So in this function, one thing that you need to find, and this is also an interesting point, is that this function can return two types of containers depending on the scenario. It can return either a bitmap container, which is on line number 10, or it can return an array container, which you can see on line number 15, depending on how big the result is of the intersection. So I know this is, it's a lengthy algorithm, but it's quite simple if you see the steps and the conditions. But I'll pause here if there are any questions on this algorithm of taking an intersection of a bitmap container with an other bitmap container. Right, and again, if everything's clear, feel free to put a thumbs up in Discord. That just helps me know everything is going good for everyone. Perfect. So that's great to see. So this covers one of the three cases for intersection, which is a bitmap with a bitmap. And now we come to the last case, which is again the heterogeneous case, which is an array container with a bitmap container. Now, the reason why this case is special, right, is because again, you need to make an observation, which is the intersection of an array container and a bitmap container is always an array. And again, I'll repeat this so that everyone has a moment to think about it, because this is again a very important observation that should come through, which is whenever you take an intersection of an array container with a bitmap container, the result is always an array container. Always. It cannot be a bitmap container. It has to be an array container, the result. The reason is because, again, an array container has less than or equal to 4096 elements. So even if all the elements matched in the intersection, your result would still be less than or equal to 4096 elements. And we know that based on the rules of the roaring bitmap, if you have less than or equal to 4096 elements, you need to be an array container. So in this case as well, the intersection cannot be greater than 4096. It has to be less than equal to. So the result will always be an array container. And this is an important observation, because with this observation, we can very easily calculate the intersection values. So what we do is that we start off with the array, which is one of our inputs, and we iterate through that sorted array. Again, we know that arrays are always sorted in roaring bitmaps because that's the way they are designed. What we do is that we take that element in our sorted array and we check if it exists in the bitmap. So we're just going and seeing if that particular bit position is set in the bitmap or not. Why do we do this? Because we need to calculate the intersection. We need to know if this value is present in both the containers. So that is why we are doing this. Take an element from the sorted array, see if it exists in the bitmap that we have. Then what we do is, if it is present, if the value is present in the bitmap, that means it's present in both the containers, then it passes our intersection condition. So what we do is that we take that element and we write it into an array container, into a new array container, right, which is our result. So that's all is the steps here, that we go through the array, check if it's present in the bitmap, so we know that it's present in both containers or not. If it is present in both containers, that means it passes our intersection condition. So all that we do is we take the value and we just put it in our resulting array container, the resulting sorted array container. And that is the intersection operation for array containers with bitmap containers. So once again, I'll just zoom out here and I'll just pause if there are any questions on the intersection operations, any of the three, array with arrays, arrays with bitmaps, or bitmaps with bitmaps, or on this observation as well. Feel free to unmute and ask. Right, so I can see some thumbs ups and there are no questions also on chat. So that is good. So with that, we are actually, if I zoom out and just to like show everyone here how much ground you have covered by sticking along, we've actually covered a lot of things. We have covered, again, I know you can't read anything at this level, but it's just to show you how much information we have covered and how much you have learned till now. So we started with the basics, we came to bitmaps, then we saw roaring bitmaps, we saw the example, and then we also went through the specifics and we understood the different algorithms or the operations that are possible as well. So there's a lot of things that we covered, and sticking along to this point in the session is really commendable. And this is pretty much all the operations that and all the things you need to know about roaring bitmaps. I mean, if you understand everything till here or have a good familiarity with the concept, you can actually implement it yourself as well in any language that you like. There is nothing in this data structure which is specific to say only C++ or only C. You can do this in any language you like. You can do it in Python, Java, even Rust or Go if you're interested. It's completely easy to implement in any language you like. There's no restriction. There's nothing specific that this data structure uses. So to close off on some final points, the one thing that we all want to see is how does roaring bitmaps perform in real life, right? Like what is the performance of roaring bitmaps compared to competitors and even to a normal bitmap? Because remember that roaring bitmaps is supposed to be better than a normal bitmap. So how does it compare? So for that, there are some interesting graphs that come from the paper again, which I'll just zoom in a bit more. Yeah, this I think should work. So what we have here is we have some measurements on the performance of these different solutions across different density. So you'll see this word here, density, showing up everywhere. What density essentially means is you can think of it as how many values are stored in the particular implementation of a set. So if there are a lot of values, the density is very high. If there are very few values, the density is low. That's all. So that's all density corresponds to, that how many values are there in your set or your implementation of your set. And the time is just telling you for that particular operation how much time it takes. So you can see here that for graph number C that we have here on the left, which is for intersection, you can notice that for a bit set, as the density increases, that means as more and more values are in your bit set, the performance is getting better, right? The time it takes is reducing. And that is expected because remember that a bitmap or a bit set is very performant when most of the bits are set to 1. That means when a lot of data is in the bit set or the bitmap, then the performance is good. But when the density is very less, that means there is very little data in your set. You can see how bad bit sets perform. You can see in the extreme case, if I just zoom in a bit more, you can see in the extreme case where very low density is there, you can see how the performance is for a bit set. You can see it's taking most amount of time at 10 power 7. And we have roaring as well. You can see in the blue line with crosses. And you can see the performance is quite decent. When the density is very less, that means there are very few elements, you can see the performance is the best compared to all other options. And after 2 to the power minus 7 density, you can see the performance is a bit less than compared to a normal bit set or bitmap. But otherwise, it's like the best of the rest. It's better than all other options at least. So if you have a lot of data which can vary in density, it's probably better to use a roaring bitmap on average, because when the data is very less also you'll have good performance, and when there's a lot of data also you'll be very close to a bit set or a bitmap. The performance degradation or the performance loss is very less. So that way roaring bitmaps is very impressive in terms of being best of both worlds basically. You can also see for the union operation it's a very similar story, that bit sets are initially very bad in performance, they are the worst actually, and then when data is more and more put into the bit set the performance improves to become the best. And again, roaring you can see plays the best of both worlds. When data is very less, also it's efficient, and when data is more, it becomes second best to a bit set. So that way, it's able to play the best of both worlds and give you very good performance on average. Similarly, you can see for insertion and removal, which are the other two operations that remain. It's again a very similar story. You can see it here on the left for insertion, and even on the right for removal. That either you are better than a bit set when the data is very less, or when there is a lot of data, you are just second best to a bit set. That's it. But you're better than all the other options that existed in the past. So that is the overview of the performance of roaring bitmaps. And you can see really that based on these measurements, it's a very good option for people who have very different data requirements. Like the data can be a lot, it can be very little at times, but and you want overall good performance. Roaring bitmaps fit the requirements very well. And the numbers and the graphs are to show for that. So once again, I think this covers the entire performance section. And we have seen here or even proved here that yes, roaring bitmaps are a good solution and they solve a lot of the pre-existing issues. And this also in a way explains why they're so popular and why they're used in so many production applications, right? Like a few others such as Apache Spark, ClickHouse, Elasticsearch, Netflix also uses this, and so on. So it's very clear why they use it now because we can see the performance is very good. So I'll again pause here if there are any questions on the performance or any part of the graph which is not clear, or any particular graph you want more discussion, we can do that now.
Is the roaring bitmap in comparison to the bit set?
Right. So again, so for that mainly we talk about the compression, and the reason why we do that is because when you look at a normal bitmap, if you have very little data, that is your density is again very less. Normal bitmaps or bit sets, again you can use the words interchangeably, they are very inefficient because you'll have lots of zeros, lots of data which is just zero, and very few ones. So again, just to take the same example of 5, 1 million, and 1 billion, you'll need almost 1 billion bytes, which is about like 1 GB approximately, to actually store that much data. And that is very inefficient. Think about it. 3 values you wanted to store and you are storing 1 GB worth of memory. So that inefficiency is very bad. But when you come to roaring bitmaps, taking again the same example of 5, 1 million, and 1 billion, you can imagine that there are just 3 elements. So we're just going to use array containers, which we discussed earlier. And if you're just using array containers, you'll have maximum 3 times 16 bits. So that is 48 bits. With again, if you add some bookkeeping, it'll be maybe 80, 90 bits. That's it. So the space efficiency gains are immense. And just to emphasize on that, if you see the two graphs on the top, the one on the left and the one on the right, you can actually see that when the density is very less, there are very few elements in the set, bit sets are very bad. Like you can see the gap between them, between a bit set and the competition. It's huge. The performance is really bad. Only when more and more elements are inserted into the bit set does the performance get acceptable compared to the competition. But if you look at roaring, that is roaring bitmaps, which we discussed today, it is the best all the time. It is number one when there are very few elements, and as you add elements, also the performance stays very good. Even better than a bit set. You can see that even towards the very end, when there are a lot of elements, roaring bitmaps are still slightly better than a normal bit set or a bitmap. And same can also be seen on this graph. If there's very little data or a lot of data, both cases, roaring bitmaps is able to outperform not just a normal bitmap, but even the competition by a huge margin.
So the exam. So in the algorithm, we discussed that with the maintain those containers.
Right. So just to repeat the question once for the recording, which is that we have discussed about containers, the array and bitmap containers, and there we only store the least significant 16 bits. I'll actually probably to explain the question better, I'll even go back to that diagram where we split the number into two parts. So that we have over here. So the answer to that particular question is that the most significant 16 bits are used to select a container, and again the container has to be stored somewhere or in some or there has to be a pointer to it somewhere, so that is stored in a separate array. So it's basically a top level array which stores each of these 16-bit values. So you can imagine it
So,
as, oh, go ahead.
so essentially, we would have what 2 raised to power 16 minus 1 containers, pointers to containers.
So that would be, but again these are the most significant bits, so it's very rare that you will have those many values, because again, if for example, just to take an example, if you have from 0 to 2 power 16 minus 1, those are your elements that you're inserting into your into your set, into your roaring bitmap, they would only have one entry on the most significant bits array, because for 0 to 2 power 16 minus 1, the 16 most significant bits are all 0.
Mm-hmm.
So maybe I can show it like this. So say for example, you have a range of, say your input, specifically your input is from 0, so is from 0 to 2 power 16 minus 1. So 2 power 16 minus 1 is basically all ones. So I'll just copy this 4 times and I'll just delete this. Yeah. So all these values in this range, right, will all go to one container because the most
Right.
significant bits are all the same.
Mm. But what will be our worst case? It will be at 2 raised to power 32 minus 1, right?
2 power 32 minus, no, it'll be 2 power 16 minus 1 on the top level array,
Uh,
because the top level array only has one entry for each most significant bit, each most significant bit value, 16 most significant bit value. So you can imagine you'll have one entry for 0, which is essentially these all bits set to 0. You'll have one entry for 1, which is all these bits but with 1 here, and so on.
mm.
So you can think of
So
it as a
we,
separate array.
in the worst case, we will have 2 raised to power 16 minus 1 containers.
Yes, that is correct. 2 raised power 16 minus 1 containers. That's right.
But all of them might not have been initialized based on the set that we are trying to insert.
Exactly. Those are initialized lazily. So initially
Right.
your top level will also be of size 0, and as you add elements, it will grow or shrink. That's correct.
Mm. So there won't be the same worst case like bitmap, right? Like 0, 1 million, and 1 billion that requires 1 billion bits, but there won't be a similar worst case for the number of containers.
No, that will not happen. And the reason why that worst case of um, more data being used compared to a normal bitmap will not happen is because of the way we would store our containers. The containers would not be 16 bits wide. I mean, they would not be array containers if you fill up a roaring bitmap. They would actually become bitmap containers because the amount of data that you're storing is a lot. So, in other words, what I mean to say is if you had a roaring bitmap with you and you filled it with elements, that means you just added all the elements in the universe into it. What would happen is that your individual containers would just be bitmap containers, right? They would just be
Mm.
1 bit per element. And the authors even give a calculation for this. There's a bit of math in the paper, but the calculation essentially boils down to this one statement, which is on average, every number which is in the roaring bitmap will take 16 bits, 16 bits on average, not more. So that is the calculation that they've given. So you can imagine that the space efficiency that way is quite good that they have maintained. Because you're storing 32-bit numbers. We should recall that the inputs are all 32 bits, but you're able to keep the average size of a number as 16 bits only because you're chopping off one half and you're keeping that as common on the top level.
Right. Thank you.
Thanks. And that was a really good question because the space efficiency part is something which initially does feel a bit confusing because you have these two data structures. You have this top level array, which has the most significant bits pointing to the corresponding container, and then you have the least significant bits. But one always interesting observation that comes across is that you're not storing the entire 32 bits, you're just storing the 16 bits for every element, and the most significant 16 bits are actually common, right? It's actually common to all the values in that 0 to 2 power 16 minus 1 range of your least significant bits. So in this case again, right, from 0 to 2 power 16 minus 1, all of them will share the same entry on the top level array. So the savings are quite a bit. And just building on that, in no matter which case on average, it's just 16 bits per number on average. So the efficiency is quite good because you're storing numbers actually double the size, 32-bit numbers.
Right, it's become like a 2D array of 2 raised to power 16 minus 1 rows and columns.
Yes, but I would say a more refined way to think about it, especially keeping in mind the space constraints, is something very similar to separate chaining that we learned in hash tables or hash maps. I'll just zoom into this to make this point clear. So the idea is something like this: that you have your top level container where you have your one entry for each of the possible 2 power 16 um, elements. Basically, maybe I know this is a bit of improvising here because I don't have the diagram directly, but let me just take a copy here to make the mental model very clear of how you can think about or visualize essentially your roaring bitmap, the two layers of the roaring bitmap. So the way you think about it is that the first layer, that is this buckets here, right? These are actually for your 16 most significant bits. That is the ones marked in red. So for example, here the 16 most significant bits are 0. So at index 0, your container is going to be present. So you can imagine that your, hold on, how did I get here? Yeah, your container is going to be present here. So we take, say, this as an example, and you will have your container here. And this is going to point to the container, and I can mark it as green. So all the values, and I'll just show the range here to make it clear. I'll just make this 4 zeros and just do this, right? All the values in this range, right, which share the same 16 most significant bits, as you would notice, they all the values will go into the same container. All of them will go into this container. So I'll just put the arrows here as well. And as you would imagine, if the container has more than 4096, it will be a bitmap container. Otherwise, it will be an array container. So this is your top level array that you maintain, which is basically indexed by the 16 most significant bits. And again, it's a dynamic array, so it's not a fixed sized array. It will grow or shrink as you add elements with different most significant bit values. And that way it stays efficient. So,
but in that case, wouldn't be finding the right container require the whole traversal of the array?
So if you want to search for a particular most significant bit, that is a particular container essentially, we again take advantage of the fact that roaring bitmap keeps its arrays in a sorted order. So it'll just be a binary search. Take the most significant 16 bits, do a binary search on the top level array, which is basically this thing, and find the position if it exists or not.
But what will happen when creating a new container in the middle of the array? That will require the shifting of all the containers to the right.
Yes, if you're adding a new 16-bit pattern that wasn't there earlier, it will be a new entry in your dynamic array, which is absolutely right. And to keep it in sorted order, you will have to shift some array elements around on average, which is O of n. But again, the authors note here that because the size of this array will not be very large, it can actually fit in memory. Because
The worst case is 2 raised to power 16 minus.
you will have to shift 2 raised power 16 minus 1, no, 2 power 16 minus 2, I think. Yeah, because you have 2 power 16 minus 2 elements, you're adding the last one and you have to shift everything. That's right.
Right, so can't we just make this
So the reason we can't make it a bit set is because each of these entries, which is there in the top level container, has to have a pointer to the underlying container also. So this is actually like a node you can think about that has obviously the MSB bits, the 16 MSB bits, and the pointer to the container underneath. So it just can't be one bit. That is the thing. It has to have that pointer to the container.
Yeah, right. Okay, understood.
So in a way, one way to think about it is that the top level container will always be an array container. This level will always be an array container, but yes, we optimize for space by only storing elements we want, and we binary search through it and so on. And one other point I think worth highlighting here, which also we saw in different operations in this paper, was that even though sometimes the complexity might be O of n, which we see in asymptotic complexity, you need to remember the size of the data also matters. Like what is n, right? What is the worst case size of n? And if you notice, the worst case size of n can be 8 kibibytes of data, which is quite large. Like if you look at today's CPUs, which you get in your phones, in your desktops, in your laptops, 8 kibibytes can all fit in your cache. Everything will just fit in your cache, and we know that cache is one of the fastest pieces of memory, which is very close to your CPU. So these operations also become very efficient. Your CPU is not idling or stalling. It can very quickly have all its cycles filled, and it can do these number shifting or bit shifting operations. So that is also one of the reasons why these sizes also play a role. So 8 kibibytes is not arbitrary, it's not random. They have been specifically chosen for these cache efficiency and so on reasons. So that's another point that I think should always come to, that don't just fall for the asymptotic complexity. Think about what n could be, and if n is not very large, can it be very optimal based on your CPU size, the memory size, and so on? Because those things make a real world difference.
So, by that, a single container can fit in memory, but
Yes,
the whole roaring bitmap cannot fit in memory,
the roaring, no, the whole one probably won't. But good sections of it can fit in memory if you have like continuous access or so on.
right? Right, yeah. You could cache it.
That is true. I think if you think about it, your spatial locality is 100% there, because all the elements, for example, in this range, from 0 to 2 power 16 minus 1, they all will be within one container. So if your CPU fetches the entire container from memory and puts it in cache, and you're also sequentially accessing your roaring bitmap, it'll be a cache hit almost every time, and it'll be very, very good for CPU performance. So yes, it does take advantage of your spatial temporal locality.
And we could probably have some LRU or C caching in some.
True. Yes, the CPUs will definitely have a field day on this one. I mean, optimization is very, very high. That's true. And I think with that, we have covered the entire whiteboard. So this covers everything you need to know about bitmaps, from the intuition to the implementation to the internals. Um, I think we have just about 10 minutes left. I also have an implementation of roaring bitmaps in Rust, which I can just show you here. So this is actually roaring bitmaps in Rust. And I won't go through the details of it. We don't have that much time. I will share it on the GitHub link. But just some points that I wanted to share here again is you need to always keep certain things in mind. So, for example, if we talk about that algorithm which finds the bitmap to array container conversion, right? So that we can actually see here as well. So if we look at
Your
it,
screen is not visible, you're still seeing Toronto tile.
oh, let me share. I think I have to just stop this share and do a new one, which is not an issue. So stop this and share again. And let me share this window. All right, let's see if this works. Ah, perfect. So here, let me see if I can just come to that. I'll see if I can come to algorithm 2, which was the one where we got the indexes of the set bits. I think that should be somewhere at the bottom. So this is an entire implementation. I can even run it in the end. It has test cases and everything of how you would implement this. So union, okay, these are all the union operations, union of bitmaps, These are some other things that I tried. Then we have right. I think if I search for the operation, it should be there. Count. Right. I think this is the one where we have, yeah. So this is the algorithm that we use. So we have a bitmap, which is I've taken as a 64-bit integer. And what is essentially happening here is that I have my list where I'm going to store the indexes that I get. And I'm just setting a capacity for efficiency reasons so that the vector doesn't have to keep reallocating as I add elements to it. And you can see the same operations. You can see this t and t minus 1. This is another way of writing t minus 1. It's the 2's complement. Some of you may recall from computer organization the concept of 2's complement. That's how negative numbers are represented in computers, and you can write 2's complement like this also. It's just the same thing. It's as good as writing minus of bitmap. The reason I have not done minus of bitmap is because I've used an unsigned number, and negatives of unsigned numbers don't always work well. So I've written it another way. So it's the same thing, just another way. Otherwise, it's all the same. This is the algorithm that you would remember as the pop count algorithm, which was the bit counting algorithm which I showed in the whiteboard. So I'm just counting the number of trailing zeros. This is again just a specialty of Rust that it allows me to directly count the zeros instead of getting the ones and then counting the ones. This is just again a language feature, but I had a chance to look underneath the implementation of this, and it does the same thing as the paper does. Just it gives me a easy function to call. So I just use that instead. So this is just giving me the number of zeros that are before my least significant set bit. So that gives me the index, which you can see here. And once I have my index, I'm just pushing it into my list, which I created in the beginning. And then I'm removing my least significant set bit, like we saw in the paper, which was wn minus w. Sorry, wn w minus 1. So that's the same thing done here. And then I'm just returning the list. So this is actually a working implementation of that algorithm too that we saw in the paper, which is very efficient. And I even had a chance to check that in case of Rust, when you're compiling it, it will actually use the efficient CPU instruction underneath to give you that one cycle performance of getting the number of set bits or the number of set bits, because this underneath does that operation from the paper. So this is that algorithm. And all the tests here are there. So just usual tests, right? Like you add stuff into a container. If I just come to the bottom, doing intersections, unions, and so on. So this is just the implementation. It's all in one file, the code and the tests. And I think I didn't even hit 1,000 lines, about 700 lines, 695 to be exact lines of code with the tests and everything. So you can actually see the implementation, how it's done as per the paper. And I'll share this as well so that you have a reference of how an actual working implementation would be based on what we discussed today. And that's all there was to discuss today. I think we have 5 minutes left. So if there are any questions, any comments on today's session, feel free to unmute and chat or share. I'll just share the whiteboard screen again. Right. So any questions on the implementation or anything we discussed, feel free to ask. And if there's nothing, we can also close the session early. So anything works. Perfect. We got a few thumbs ups. Again, if things are clear, feel free to put a thumbs up to mark that you're good. Any questions, again, feel free to ask them here or put them in chat. And one thing I would again appeal, there's few people who do reach out after sessions with questions, and it's really great to have that. Just want to reiterate it here that if you have any questions even after the session that you were thinking about what we discussed and you had a edge case in mind that wasn't clear, or certain implementation details weren't clear, you can always feel free to reach out on Discord. And yeah, if today's session motivates you to try implementing roaring bitmaps on your own, that's obviously a big win. Um, because these concepts aren't very difficult, though they are mostly discussed in research papers and so on. They're not difficult at all. When you break them down, they become easy to understand and they become very reasonable. That okay, why does it exist? Why did someone think of this? And why so many people use it? A lot of the nuances become very clear at that point.
Does Redis have a implementation of roaring bitmap?
Um, as per my reading, I wasn't able to confirm this, but but there are databases that use roaring bitmaps underneath, or search engines that use roaring bitmaps underneath, like Search. If you'd have heard about it, it's again a search uh, product that uses it. InfluxDB uses it. Elasticsearch uses it. So I think maybe Redis might be using it as well underneath. I wouldn't be surprised if they were.
Give an interface for us to use it.
I guess so. I believe that would be correct. Probably they're using it internally to make their other operations or APIs efficient. Yeah.
Yeah. Just trying to think in absolute terms, maybe it's repetitive, but I'm trying to see how better roaring bitmaps are in terms of memory in comparison to the original bit sets, right?
Right.
So if you want to store all 32-bit integers,
Mm-hmm.
it will, in a normal bitmap, it will take us 2 raised to power 32 minus 1 bits in the memory. But if
Yeah.
you were to,
Correct.
yeah, yeah, but if you were to store all of that data into roaring bitmap, how much exact memory would that take us? Like 8 KB for every container, and we will have what 2 raised to power 16 minus 1 containers.
Um. Yes. To summarize, yeah. So we would have 2 raised past 16 minus 1. Sorry. If the problem statement is that we want to store all 32-bit numbers in a roaring
Yeah.
bitmap, um, yes, you would have 2 power 16 possible MSB bit patterns, and each of them would have an entry on the top level container. Then you would have individual containers on the lower level, which would in our case be all bitmap containers because we are adding all the 2 power 32 possible numbers. So each bitmap will be of 8 KB bytes, and 8 KB bytes means that it stores our 2 power 16 numbers. Um, yeah, it stores all the 2 power 16 LSB patterns. So yeah, it would be 2 power 16 times 2 power 16, which would be 2 power 32. Yeah, because yeah, yes, because the exponents add up.
So is that the same exact requirement, right?
Yes, we wouldn't overshoot the space that a bitmap that a normal bitmap would take, which should be expected because if you're adding all the numbers in your set, you can think of it as all your bits are set to one. And the fact that roaring bitmaps doesn't take extra space compared to a normal bitmap or a normal bit set is really really good, and it makes it versatile that way.
Yeah, yeah. I was trying to think that only. Great session. Yeah. You put in a lot of effort into this. PPT was really intuitive.
Thank you so much. It means a lot, and I think for all the sessions, um, having this PPT really helps. And even as you work through building them, it feels very intuitive. Like it's very simple to put what's in your mind on this. I found that slides don't work as well. Like if you were to take this and make equivalent slides, it would either be too many slides or it would be difficult to just present the information. So yeah,
I mean, you are the first person I'm seeing using this method of presentation, drawing everything on draw.
yeah, I've not. Yeah, I've only seen few people in Excalidraw, but yeah, Draw.io was definitely a new experience, and it's definitely been good. I would encourage a lot of people to try this approach as well. Like I think in terms of presentation in general, especially for technical topics, going beyond a PPT is something at least in my experience, should be encouraged. And I'm really happy to hear that it's working out. At least this experiment that I'm trying.
Yeah, it's great. So cool. Thank you.
Perfect. Thank you so much, everyone. It was a great session, and with this, the 2024 sessions are done. We will convene again in 2025 with a new poll to discuss another technical topic. the stuff that we discussed today, I will share it on GitHub, obviously the whiteboard and the Rust code. And also the recording will be shared on YouTube soon. And again, all this will be notified on the Discord channel once it's ready. So once again, thank you so much, everyone. Have a great evening. Happy holidays.
Thank
Bye bye.